Okay, good morning and welcome back. Many people care about the first quiz this Thursday. So I will quickly explain how to conduct the experiment, how to conduct the quiz. It will be a take-home exam. I will upload the file to ILMS very soon. Yes, very soon. Maybe today. Okay, so you can write your answer. You can type with computer or handwriting. It's okay. Be sure to convert the file to PDF format and upload your answer through the ILMS system before Friday. Late submission doesn't count. That means if you submit your answer 11 o'clock or 10:10, doesn't count. So make sure you will submit your answer before 10 o'clock. Before 10 o'clock. So you probably have at least 1 or 2 days, maybe three. The time is sufficient. And of course, it's open book. Open everything. You can discuss with your best friend. Anything is okay. Okay. So that's quiz number 1. So you don't have to come here next time. You don't have to come here. Okay? This Thursday, you don't have to come here. No one will be here. Okay. Any other questions? No? So we will continue our discussion about modes in cavity. It's quite similar to the waveguide. The starting point is exactly the same. We will talk about modes in cavities. Okay? So let me show you first. This is a cavity. You can open this cavity and have a closer look. This is the interior of the cavity. This is a special designed cavity, not cylindrical cavity. It's a very special designed cavity. With this cavity, we can measure materials permeability with very high accuracy. So it's a pretty interesting cavity. Okay? Designed by our, not designed, but measured by our TA Cai Zhenghong, previous one, Cai Zhenghong. He measured the material property and published this paper very quick, very efficiently. Published in APL, maybe after experiment, so very efficient. So have a closer look at this cavity, small cavity. This cavity is quite small, however, it's not TE mode. It's somewhat like deformed TM mode, or a combination of TM and TEM. So it's a hybrid mode. Hybrid mode. Let me tell you the truth. No one tried to derive the EM field distribution, the field pattern inside the cavity, because it's impossible. You cannot separate them. You cannot use separation of variable to separate everything. and found the E field and found the B field. It's impossible for this structure. You can have a look. So how to do that? Computer simulation. We use computer to simulate the EM field profile inside this spatial cavity. Very spatial, very interesting cavity. So have a closer look. Be careful. It's a mushroom type. Maybe I should draw the cavity for you. That's a regular cavity, but that cavity is a little bit. It's a mushroom, like a mushroom here. So E field will be here because of the boundary condition. So electric field close to the center conductor will be 0. Therefore, close to the center conductor, only magnetic field. So we can separate E field and B field. That's our purpose. No one do that before. We can separate E field outside, B field inside. So it's a new structure. With this structure, we can measure mu, r accurately. Okay, and interestingly, we use some kind of magnetic material and some kind of narrow particle. Narrow silver particle. And interestingly, the behavior will be less than 1. Sometimes maybe close to 0. So it's very, I think it's very interesting. Okay, so this cavity. Without this one, it's easy. Just cylindrical cavity with both ends closed by conductors. So we will start by a rectangular cavity. Rectangular cavity. That is a rectangular waveguide with 2 ends, just one end and the other end, closed by conductor. 2 conductors, for which we have 2 additional boundary conditions because of 2 ends. So let's consider the fundamental mole. That is TE mole. TE mole, TE10 mole. So EZ will be like this one. So it's a propagating wave for waveguide. However, we want to determine the coefficient C plus and C minus. Exponential IKZ Z minus I omega t, which means forward propagating wave. And on the other hand, KZZ plus omega t is backward propagating wave. So we will have 2 waves. One is propagating forward, the other is propagating backward. And because of the boundary conditions, at this end and the other end should be 0. Especially HZ, because it's normal magnetic field, it should be 0. Tangential magnetic field is not 0. For example, X equals, just a moment. Just imagine This is the z direction. So x, y, x, y, z. Okay. X in this one, what is the definition? X, y, z. Okay. X, y, z. So hz on this surface, on this surface, on this one should be 0. And not necessary to be 0 because hz is cannot, according to the boundary condition, hz is non-zero. But hz at this point, this surface is a normal. Normal B field should be 0. Normal B field should be 0. Therefore, you can expect that at this point it should be C plus equals C minus because Z equals 0. Z equals 0. And exponential minus I omega t minus I omega t. So C plus plus C minus 0. Therefore, C plus equals minus C minus. That's the first boundary condition. We still have another one. Another one allows us to determine this one. Because there is a minus sign, so this one becomes sine. So kz, on the other hand, the other side should be 0. So side 1, z equals 0, g equals d should be 0. According to the boundary condition, we know kz will be quantized. This one determines the coefficient. This one determines the wave number, kz. Okay, so kz will be quantized. Okay, so the final result will be exponential minus I omega t, the same here. And cosine, sine. Okay. And interestingly, n runs from 0, 1, 2, 3. 0 doesn't matter. However, 0 doesn't matter, but L must be at least 1. If L equals 0, nothing, trivial solution. So L must be starts from 1. Okay, so it must be starts from 1. Substituting into equation 32, we got this one. So, see, resonance frequency is quantized. So that's the resonance frequency. And we will have many resonance frequency, many combination, N1, 0, 1, 2, 3, N0, 1, 2, 3, L, 1, 2, 3. So we will have infinite number of resonance frequency, infinite number of eigenvalues in this case. That's the resonance frequency, infinite number. Count these. But normally we prefer the lowest because for the lowest it's much easier to control. But if you are unlucky, you operate at higher mode, then probably you have to consider all the possibilities. All the possibilities. That's a big challenge. Okay, so have a closer look. Now, xz becomes quantized. And compare with a string. Just imagine we have a string, a wire from this end to the other end. And then we pull here and release, let go, doing. Fixed end, okay? So it's quantized. So in this case, just propagation in the z direction, the wave propagate and bounce back and propagate, okay? So independent variable, just z and t, and the mode number L will be quantized. So the fundamental mode L equals 1 is sinusoidal, something like that. And L equal 2 is something like L equal 3, going, that's L equal 3. Okay? 1, 2, 3. Because S and Y is not quantized in this case, in the string. However, for this case, for three-dimensional cavities, EX, EY, BS, BY, EZ, or BZ are quantized. So we have three variables, and S, Y, Z are quantized. Give us the quantum number M, N, L. So M, N, L is the quantum number, similar to quantum number because of the boundary conditions. Boundary conditions give us something very similar to quantization. Okay? The problem is this one, that principal quantum number, angular momentum quantum number, magnetic quantum number, we still have one spin quantum number, right? Compared with the hydrogen atom, we still have another last one. But time is not quantized. You cannot quantize the time. So how to do that? No one knows. Even Einstein do not have an idea. So if you have time, maybe you can study how to find the relationship between Schrödinger equation and Maxwell equations. That's very interesting, very challenging. I don't know. At least not from the present Maxwell equation. But how to do that, I have no idea at this moment. I just tell you, S, Y, Z, because boundary is quantized, so we have three quantum numbers. But I don't know how to, looks like T should be quantized, but time is, I cannot explain. Any comments? Yeah. I don't know how to explain spin quantum number. How to explain the last quantum number. Looks like three-dimensional structure plus time, 4 variables, but we still have 3 quantum numbers. Okay? How to generate the last one? How to generate the last one? I have no idea. Okay, next one. Let's consider a closed cavity. What is the most important factor for the closed cavity? Eigenvalue. Yes. So the most important one is the resonance frequency. What else? What else? In addition to resonance frequency, what else? Okay, let me show you. What is the function of the cavity? Cavity is not, cavity also means 蛀牙。蛀牙是一个 cavity， 这个也叫 cavity。你经常来看蛀牙也叫 cavity。我讲当然不是蛀牙。A closed cavity. The purpose of the cavity is to store EM field, store energy. That's the purpose of the cavity. No, just like reservoir. 包山 reservoir or small 包山 second reservoir. So it can store energy. Reservoir can store water, but this one can store EM energy. But energy will lose because of conductor. It's not perfect conductor. So energy will gradually decay because omega loss, because conductor loss. Okay? So the problem is how long can we store the energy inside a cavity? We will have 2 strategies. One is we inject a signal inside the cavity and see the cavity's frequency response. The other is just like we excite energy inside and see its time response. So we will have two strategies from frequency domain or from time domain. They are correlated through Fourier transform. Through Fourier transform, yes. But different viewpoint will give us different result. And we want to find the difference. Okay, so let's consider the simplest one. The definition of Q. Q means quality factor. Q represents the resonance, the quality of a resonance condition. So far we assume a real omega for EM waves in an infinite space of a waveguide. Since the fields are stored in a cavity, it dampens in time, exponential decay in time. If there are losses represented by a complex omega. Okay, so we have two viewpoints. First, we control the frequency, one frequency at a time, and the frequency is always real. Controllable, that's frequency domain. Okay, so for frequency domain, we just inject a signal with frequency omega 0. Okay, and we will see its exponential decay, sinusoidal, and no loss, no loss. Okay, conductivity is infinite for perfect conductor or superconductor. Can you tell me what's the difference between superconductor and perfect conductor? Which one is better? What's the difference? Superconductor, perfect conductor, Superman and perfect man. Which one is better?
Perfect.
Okay, superconductor and perfect conductor, their conductivity is the same. Infinite. Infinite. Conductivity the same. But their magnetic response is different. For perfect conductor, no magnetic response. For superconductor, we will have Masonry effect. The magnetic field cannot penetrate a perfect conductor. Okay, but for superconductor, magnetic field can penetrate the superconductor. No difficulty. That's the major difference. Magnetic field. Electric field, their response is the same. Okay, so actually no perfect conductor at all. No such conductor. Just superconductor, no perfect conductor. Perfect conductor is an ideal case only. Okay, which can find superconductor only. Okay, but since the conductivity is not ideal, so we will consider finite conductivity. In that case, it will exponential decay in time. Okay, so we will add these terms and these terms. Let me explain what's the physical reasons for delta omega. We add two terms, delta omega and omega 0 over 2q. Okay, the physical reasons for delta omega. First is because the cavity, the size of the cavity is slightly changed. Because wave can penetrate into the cavity slightly. So the dimension of this one is about 10 centimeters. But remember, the EM wave can penetrate slightly. That's called skin depth. Skin depth may be 1 micron or 2 micron or a few micron, depends on frequency. So it can penetrate slightly. Looks like the cavity enlarged a little bit. The cavity, the waveguide slightly larger, slightly, just slightly. Okay, so in general, because we have a minus sign, so this one will be slightly larger. Resonance frequency will become slightly lower, just like the length is slightly larger. So resonance frequency will be slightly lower. Therefore, delta omega should be negative. Keep this in mind. Not always. Not always. Depends on the field patterns. Sometimes it will be positive. Not always. Okay. Depends on EM field patterns. Sometimes you, just like the cavity over there, you insert something and the resonance frequency is not increase, but decrease. We are very surprised to find that. The fundamental mode resonance frequency is high, but when we insert a mushroom-like material inside, the resonance frequency is not increase, but decrease. Decrease. Because it's a coupling between two waves. It's a deformed, it's a hybrid mode. So depends on field pattern. Not always true. Second, for Q, because energy will lose, so field will exponential decay in time. Okay, exponential decay in time. So let's represent exponential decay rate. Omega 0 Q. Omega 0 times T is constant. And Q will be dimensionless. From this viewpoint, dimensionless. Q just a number. Okay. So let me write the total energy. Total energy stored in the cavity. We use the notation called U, stored energy. So it's well proportional to E field squared. So therefore, E squared is E times complex conjugate. So eventually we got two imaginary parts. So it will be exponential decay. So energy will depend on initial energy and exponential decay energy. Okay. So just imagine at time 0 we have stored energy inside, and let go. Energy will exponential decay because of the conductor loss. It will exponential decay. So time change rate will become du over dt minus omega 0 over q u. That's the power loss. Energy consumption rate, that's the power loss. From this equation, we can rewrite Q becomes minus omega 0 u over du, u over dt. So quality factor will be equals to the resonance frequency, resonance angular frequency, times stored energy, divided by power loss. That's time dependent, time domain definition of Q. That's different. That will be different from frequency domain viewpoint. I will show you the viewpoint of frequency domain here. So time domain is easy. We store energy at time equals 0. Don't ask me how. We just do it. We store energy inside the cavity. And let go, do not touch. And energy will exponential decay because conductor loss. Okay? And we can calculate exponential decay rate. And eventually we got Q. 2 pi resonance frequency. Total stored energy by power loss. Okay. So you can imagine if I open a small hole here and then a small hole here, the energy will lose from this hole. Okay? In that case, power loss will be increased, so quality factor will be, this one increase, quality factor will be decreased. Okay? And just imagine, we have a super large cavity. If this cavity is about the size of Tsinghua University, and we open a small hole, still quality factor will be large. So if we have an extremely large cavity, quality factor will be very, very large. Okay. So higher quality factor means the energy will store inside and decay not very fast. Okay. Decay. If this one is very, very large, 10,000 for example, then decay rate will be very, very slow. Okay? If this one just 1 or 2, wow, decay very fast. Very, very fast. So quality factor just represent the quality of the cavity. I mentioned this. Next one is from the frequency domain. How to excite the cavity? Or we can rewrite field into frequency domain to convert to time domain. And we will rewrite from time domain to frequency domain. We use the inverse Fourier transform. Inverse Fourier transform. That's the frequency viewpoint. We inject one frequency at a time. One frequency at a time. Okay, so we got a frequency time response. And we can calculate frequency response from time response. Use the inverse Fourier transform. I just skip how to do that, but it should be easy. Just write it down and eventually we got this equation. From here to here should be very easy. Should be. Okay. And we got frequency response of the electric field. And this one, we want to calculate power of the frequency spectrum is best seen from the field energy distribution in frequency domain. So we, from the field energy viewpoint, see, actually, we will become, what will happen when omega equals this one, omega equals these two, then we will have the largest value, that's the maximum. When omega equals this one, plus or minus, and these two cancel with omega, and we still have this one. So we will have this one, 1/2 maximum, 1/2. So we will define the full width at half maximum. So let's have a look at the frequency response. Looks like this one. Okay, this is omega 0 plus delta omega, but we know delta omega is very small. And we will have half full width at half maximum. 半高宽度，一半的高的宽度。Okay? Full width at half maximum points, 2 point, 1, 2, above and below. Okay? So we got delta omega equals omega 0 over Q. Resonance frequency is omega 0. So delta omega is full width at half maximum. Therefore, if you want to calculate Q, just omega 0 divided by delta omega. Just omega 0 divided by delta omega. You got the Q, frequency domain definition of Q. So we have two viewpoints. For high quality factor, it must be very, very sharp. Very, very sharp. So for low quality factor, it must be very, very flat. Okay? So there's difference between high quality and low quality. Low quality factor, high quality factors. Okay? That's from frequency response. Okay, but for most of the case, we just imagine closed, but we have a small opening here, and we inject a signal into this one, and see its frequency response. If the incident frequency is different from this one, then the wave will be reflected back. However, when the incident frequency is exactly close to this one, the wave can penetrate into the cavity and store it inside. So from the frequency response, reflection, you will see something like this one. Some reflection like this one. That's from reflection response. And you can calculate full width at half maximum. Very similar to here. And this is omega 0 plus delta omega. This is delta omega. Okay. So you can, from frequency domain, you can control the frequency one at a time, and you will see its response, just like this one. Or you have another technique. You put a detector inside and detect the field, intensity of the field, and you measure the highest field and have maximum field. Then you can determine the full width at half maximum. Many techniques. Okay. That's the ideal case. However, for some case, it's not always symmetry. Not always symmetry, but that's another story. Not always symmetry. Sometimes it will distort. Doesn't matter. The physics is still the same. Okay. So the physical interpretation of Q, one is from the frequency time domain, we know Q is the omega 0 resonance frequency, stored energy, divided by power loss. So what is omega 0? It's 2 pi F0. F0 just equals the web period related to web period. So the stored energy, this part, just like a reservoir, and you open a small hole, and the water will gradually leak, okay? And the leak time, if you have one, just like this one, we have less than 1 liter, and I open a small hole. You can calculate how much time we need for this bottle to be totally leak out. So for this case, you can estimate decay time of the stored energy, and we will compare these two. So just like tau 0 web period divided by tau d times 2 pi. That's the quality factor in time domain. Okay. Have another look. That's the frequency domain. Lewis domain definition, we have omega 0 divided by delta omega. Omega 0. Actually, we have 3 omega. We have 3 notation, but these 2, this is uppercase 的 delta omega, lowercase 的 delta omega, 大写的 delta, 小写的 delta. Okay, but they call delta omega. Okay, but that's another d omega, small omega. Okay, for a lossy cavity, a resonance mode can be excited not just at one frequency, but you can excite at multiple frequency. Multiple frequency, you have a distribution. Unlike the ideal case, if no loss, the quality factor will be extremely large. The resonance condition will be very, very sharp. However, we have loss. Okay? So quality factor will broaden. That means you can excite this cavity with from here, doesn't matter. You have a bandwidth. You have a bandwidth. The problem is, for many applications, you need a wide bandwidth or narrow bandwidth, which one you like. For example, if you want a very high EM field inside, then the loss must be small. So you can inject a signal and energy will accumulate inside, will store it inside. So EM field will be extremely large inside for low high quality vector. But for some application, such as plasma, such as material processing, the source is unstable, such as your home microwave oven. The frequency is jumping, not constant. Your home microwave oven, 家用微波炉那个频率根本就乱跳。So what? The purpose is to heat the food. Jumping frequency doesn't matter. So what? It can heat. So in that case, you need a low quality factor. Okay? So depends on what you want. Sometimes you need a very high Q. Sometimes you need a low Q. Okay, depends on your purpose. Okay. For example, if you have a cavity and very high Q, and your source is unstable, what will happen? Most of the energy will reflect back. That means your energy doesn't work at all. Okay? For example, hyperfine splitting of nuclear magnetic resonance. They need a frequency exactly at 203 gigahertz. But most of the source is not tunable. It's not tunable at all. So they need a frequency with tunability. No one can fabricate a source with tunability before until our TA, Cai Zhenhong. Okay. Last year, Cai Zhenhong and I went to Japan. We conduct an experiment. We have the world record bandwidth. we have a 36 gigahertz bandwidth, the widest in the world record, the record high. So I am writing a paper right now, revise his paper. Okay, that's pretty high bandwidth. We can adjust, control the bandwidth by change the magnetic field, change the beam voltage. So we can change, control. That is frequency tunability. Okay. Before that, people can adjust 1 or 2 gigahertz. So it's about 10 times or 20 times higher. 20 times higher. Much, much higher than the previous result. Okay. Okay, let me show you how to calculate this one. That's time domain polarity factor. We will how to calculate stored energy. Stored energy, we will use this notation. Stored electrical energy and stored magnetic energy. But for a resonance condition, these two are the same. For resonance, that's required. That's required. Just like RLC circuit. On resonance, L, and C. L stores magnetic energy. C stores electrostatic and electrical energy. On resonance, these two must be the same. Must be the same. Of resonance, of course, they will be different, but on resonance, they will be the same. No matter it's series or shunt, 串联或并联, they should be the same. That's the requirement. Okay, so stored energy can be write into 2 omega E or 2 omega M. So how to calculate this one and this one? Okay, power loss, we can use pointing vector or we use surface current loss. We just use surface current, surface resistivity. After integration, we know surface current, effective surface current is related to N cross H, tangential H field. Okay? Just imagine, this is N H, if H in this direction, N cross H, N cross H, N here, on this surface, N here, H, just assume H here, N cross H, so we will have a surface current here. And you can double check with Ampere's law. Ampere's law tells us we have a current here. We will generate magnetic field here. Okay, that's correct. So you can always check with your right hand. Ampere's law, your right hand. Okay, so you know H field is related to surface current. K effective equals N cross H. You can keep this in mind because it will be very useful. Okay, so we can calculate anything. We can calculate stored energy using this one, and we can calculate power loss using this one. Okay, how to do that with that one? The cavity, EM field is quite difficult to interpret, to calculate. No analytical solution. No analytical solution. So how to calculate this one? Once again, you don't have to. You have computer. You have simulation software. The problem is simulation software is very expensive. That's the problem. Okay. Otherwise, very powerful. If you don't have to worry about the money, then you will have a better life. Okay, so just a moment. Maybe I should show you. I'm not sure. Okay? That's the permeability measurement and control for epoxy composite. This is our TA 太深口，太小化。Okay? How to do that? That's the side view of this cavity. Side view, E field, H field. Okay? You can see here, close to these regions, no magnetic field, no electric field. And I'm sorry, it's very small. Here, just magnetic field, no E field. So we can separate E field and B field. We always know E field, B field are coupled together because of Faraday's law and Ampere's law. Say they always Ampere's law with Maxwell correction. So E will generate B, B will generate E, and then couple together. But with this kind of geometry, we can slightly decouple E field and B field. And obviously, if we put material close to the magnetic field, we will have magnetic response, but no electric response. So we can separate their properties. Okay, this is the cavity. And the sample is here. Very small. Very small. And very expensive. For a small sample, you probably need, I don't quite remember, but a couple thousands. Okay, and then you can see here, we can measure the resonance frequency. That's the frequency domain. From frequency domain, we can measure its response. Actually, we inject a wave here. We use coaxial waveguide. Coaxial, SMA waveguide. Couple signal to here. We couple the signal from the top and excite the waveguide mode. Okay? And we can measure its frequency response and measure the quality factor. And from the quality factor, we can determine real part of epsilon, imaginary part of epsilon, real part of mu, and imaginary part of mu. Okay. It's a completely new idea and simple way to separate EM field. Okay. Formula for Q due to ohmic laws. OHM, ohm. Ohmic is Ohm's laws. Ohmic laws For rectangular and cylindrical cavity can be found in many textbooks. For example, Colin, Fundamental of Microwave Engineering, or POSA, Microwave Engineering. Okay, these two textbooks are quite good, especially Colin. Colin somewhat looks like from physics department, so he derived all the equations carefully. POSA from engineering department, he simplified the notation a lot, much easier to understand, so up to you. And Q due to other type of losses. Actually, the losses is not just one, but many losses. For example, the loss from conductor, you have two names, conductor loss or ohmic loss. Two names, ohmic loss or conductor loss, it's the same. And if you put some dielectric material inside, dielectric material will absorb the energy. So there will be a dielectric loss. If you put magnetic material inside, there is a magnetic loss. Okay? If you have a small hole here, energy will radiate. That's radiation loss. Okay? If you have a small hole here, energy will something like diffraction. That's another one. You will have diffraction loss. Okay? And if you want to cargo the energy into the cavity, some of the energy will be reflected back. You will have reflection loss. So many loss. Just consider the biggest term, the largest term. Okay. So all you need to do is sum all the power losses, more than one. More than one, okay? And quality factor will be interestingly, just like a series resistor, shunt resistor, 串并联的电阻 shunt resistor. This one, just like this one, shunt resistor. Something like that. Okay, let's compare the difference between waveguides and cavities. Waveguide, the purpose is, the function is to transport EM energy. But for cavity is to store EM energy, to store energy inside. Okay. And for waveguide, we have a dispersion relations. We can find the relation between omega and Kz. That's dispersion relation. And wave will propagating, and because of metal conductor, we will attenuate, exponential decay. So we will have an attenuation. And resonance frequency for a cavity, and quality factor. So for cavity, we will have two terms, eigenvalue and power loss. Okay. Examples of applications for microwave from 0.3 to 300 gigahertz. Transport of high power microwaves such as multi-cavity, multi-kilowatt waves, or multi-gigawatt, or multi-terawatt. Okay. For example, if you have a nuclear power station and you can generate gigawatt energy, and how to transfer the energy, transport the energy. That's a big issue. Normally people use waveguide. And applications, we have a particle accelerator such as synchrotron radiation. They have many cavities. I will show you the cavity used at Synchrotron Radiation Research Center, roughly about this big. 同步辐射的共振腔这么大一个 ，and bulky and heavy, quite heavy. Okay, and made of superconductor, so very expensive. One cavity roughly about ED200324. Very expensive, yeah, roughly $3 million for one cavity. For traditional cavity made of copper, just about $2 million. But for superconducting cavity, $3 million. Yeah, quite different. Okay. But for superconductor cavity, quality factor extremely high. So they don't have to worry about the competition for many modes. Okay. I will show you here at chapter 14. Last one, another application is frequency measurement or material processing or material characterization. Many applications for cavity. Okay. Last slide, let me show you this one. Let's high Q microwave quasi-optical cavities. Our purpose is to heat material very efficiently. How fast? We want to heat the material from room temperature to 100 in 1 microsecond. We want to heat the material very efficiently. How to do that? We use intense EM field, extremely high quality factor. But conductor, we will have conductor loss, and superconductor is very expensive. So how to do that? We use a quasi-optical cavity. This is a spherical mirror, and this is the plane mirror. Let me show you. This is a spherical mirror, and this is a plane mirror. So we inject a signal here. Signal will doing. Eventually, they will form a resonance pattern. The resonance pattern looks like this one. Actually, it's quite similar to optical system. For optical system, we will have more than 100 or 1,000, or the Q will be very high. But for microwave, in this case, the frequency is about 24 gigahertz, and you will form multiple spots. And EM field close here, very high. So we just put a small material here. It will heat very fast. Okay, so this is the microwave tube. This tube is developed by Professor Corey Chu, 朱国瑞院士，他们做出来的。 其实就是我们做出来的。OK，this tube can generate 24 gigabits for multiple purpose, for material processing, for satellite communications, and now it's for 5G communication. Okay, and we can monitor the power, control the input signal, and then it will amplify. And then, eventually, some of the energy will be injected to the cavity. There's a shading here, shading box, to protect the radiation. Okay. In this case, we will have reflection loss due to coupling. We will have conductor loss, plane mirror and spherical mirror. We will have dielectric loss. We will have radiation loss. Okay, so, and last one, diffraction loss. We will have multiple loss. Okay. That's the application of this cavity. Okay, the end. We still have many times. Any questions so far? Any question? This Thursday, we will have quiz number 2. And you don't have to be here. Keep this in mind, you don't have to. I don't have to be here. No one will be here. Okay, it's a take-home exam. I will upload file to ILMS, and you can download on that website. Okay. Please tell your friend. Please inform them. You don't have to be here. Okay. And you are welcome to discuss with your friend, but not TA. Not TA, not professor. Okay. With your friend, with your classmate, with your father, your mother, with your brother, everything is okay. You can use Google, you can use anything. Okay. You probably will have 48 hours, maybe more. So time is sufficient for you to finish the exam. Okay, just think about it. I will show you how to simulate. Okay, this is the simulation software. For example, if you want to open a waveguide, open. For example. questions? Think about it. Okay, just a moment. Maybe I should show you this slide first. Okay, have a look. That's excitation of the waveguide. Excitation of the waveguide. This is the rectangular waveguide mode. Rectangular waveguide mode. And this waveguide generates electric dipole or magnetic dipole on the side wall of a cylindrical waveguide. And that's the coupling. Some of the wave will transmitted and part will be reflected back. But at least most of the energy will be converted from rectangular waveguide to cylindrical waveguide. Okay? So polarization is linear. Become large, small, large, small. Actually, it's linearly polarized. That's the linearly polarized wave. Okay? Let me show you another one. If you control just like this case, if you inject the signal from the other side, 90 degrees perpendicular to each other, then it will excite circularly polarized. Okay? It's circularly polarized, right? And what happened here? The incident wave here, and it will divide it into two parts and bounce back. And then, see, the geometry is distorted. What do you mean? What do I mean? Just imagine, wave is excited here. It will be divided into this component and this component. And the components, the incident wave will be divided into two components. Just imagine a linearly polarized wave, just like this one, is divided into two components, separate, 45 degrees. And then the propagation constant for this one or this one is slightly different. So one is travel faster, the other is slower. And eventually, something looks like this one is largest, this one is smallest. So look like circularly polarized. So just like optics, they use the same idea. For example, quarter wave plane. The purpose is to generate something like this one. The incident wave is divided into two parts. And because of Kz is different, we can change the phase. And eventually we can synthesize a circularly polarized wave or a linearly polarized wave, a right hand or a left hand circularly polarized wave. For example, another one. This right-hand circularly polarized wave. Okay, the EM field rotate in this direction. Okay, so you can control the EM field. Maybe let me show you. Okay, that's another case. Just like your homework assignment, you have rectangular waveguide like this one. See, you can check your lecture note. Problem something, 8 point something. Okay, that's the rectangular waveguide. Rectangular waveguide. And this is a closed waveguide. So it's a cavity across the waveguide. You can calculate the resonance frequency. And you can simulate the EM field. It will help you to understand what's going on better, much better. And you can draw any figures you like. You can analyze thermal response. You can analyze the frequency response. So with this kind of software, this kind of software are normally very expensive. Just give you an idea, normally very expensive. We have a license in our lab. For educational purpose, it's okay. And we can draw any geometry, such as cone, such as non-uniform waveguide, such as spiral waveguide, such as anything, any geometry you want, such as this kind of cavity. Okay, spatial design cavity. So you can check the boundary conditions, the correctness of the boundary conditions. Okay, boundary condition is the cornerstone of this software because it starts from boundary conditions and match from one boundary, and normally that's finite element. So they start from one boundary and another boundary and meet at the center. So it's finite element software. So very efficient and powerful software. Okay, I will stop here. Any questions? If you want to practice, you can contact our TA. Not 蔡点学，也许许宏俊. Another one. If you want to learn how to perform the simulation. Okay, I will stop here. Let's welcome our TA. No problem. Okay.
Today no.
Happy day.